All right, let's get started. I've got JT here in the studio. I've got Bruno. I've got Lee, and we have Eli online.
Wonderful. Well, it's good to be back again, and we appreciate you continuing to listen in on this conversation with R&D. At 9 o'clock, we had talked primarily with Bruno, and we talked about a lot of things, and we'll continue a lot of those conversations throughout this hour and the next, but focusing at that point mostly around the world of 32-bit and 64-bit and what it means to get to 64-bit as well. So what we're going to do this hour, and again, any of these questions are open at any time around any of these topics, so feel free to ask those questions, and we'll try to get those asked during these interviews and during these conversations. But we're going to focus this hour mostly around compiler technology and architecture and everything in between in that regard. So I'd like to present Eli Boling, who's joining us for this portion of the conference. Eli, are you there?
Yep.
Welcome to the session.
Thank you.
So I'm starting each of these sessions by asking the main participant, in this case you, Eli, a little bit about yourself and about your experience and history working with these technologies.
Well, I started back in, early 90s, 1991, working on the 16-bit tools for Borland. Specifically, I was working on the linker. And I spent a lot of time working on the DOS extender technology that was part of Pascal, the 16 and 32-bit DOS extender technology. I did the original 32-bit linker. And then from there, we worked on profilers and other debugging tools. And ultimately, we moved on to do the first C Builder 1 project, which was the metamorphosis from C++ to the RAD tools that we have nowadays. And I've worked on and off on the linker and compiler and other tools associated with that particular product line for ever since then.
Wonderful. Well, definitely a lot of history, and especially on the technologies that are relevant to through the years and onto this new architecture and continuing to fully support VCL and FireMonkey, but on a completely new toolchain. So why don't you tell us a little bit, before we get into the toolchain side of it, from a compiler perspective and a language perspective, what were some of the things that we had to do and we continue to do to make C++ work and work well? How did we enhance the language to make it work, to provide a visual development experience, and to use a component architecture with a delegation-based framework, and all these kinds of things that were different than the way C++ previously had utilized development environments and architectures, framework architectures?
Well, there were a couple of major features. First of all, we knew that we had in the Delphi product a component framework and a model that was really good for users who wanted to build GUI apps and even non-GUI components. And we wanted to bring that forward into the C++ world. And at the same time, we also had this enormous library that was very popular, VCL. So we looked into how we could actually use the binary libraries from Delphi, and we found that we could use we could make the connections pretty well between Delphi and C++ classes, because Delphi classes are just a single inheritance model, and for the most part, the single inheritance vtables are pretty easy to access from C++.
Mm-hmm.
There were complications, though, for dealing with some of the more interesting design features like properties. properties are the handle by which you can take an element that you drop on a component that you drop on a form and customize that component at design time. And we wanted to be able to take advantage of that in C++ and participate cleanly in the design surfaces that we had with Delphi. So we found that we really needed to extend the C++ language a little bit to support that so that we could integrate cleanly with the Delphi components. So that was one of the main features that we added to C++. The other feature, main feature that we added was a notion of, call them method pointers. At the time, we called them closures, and those are basically just a pointer to an instance and a method. And those were used for all the Delphi event handlers. And those were the two major features that we exposed to the users. There were a whole bunch of other little ancillary features that we started out with for supporting the binary hookup between Delphi and C++. Delphi, being its own language, had its own semantics for certain types of objects, the way they were returned, the way they were passed around. And in order for us to bridge the gap between the C++ world and the Delphi world, we had to have a whole bunch of little extensions to describe certain special Delphi types as having special semantics. So we added in some keywords for or declaration specifiers for Delphi return types and a few other things. Those really aren't so much user visible things. So I don't really think of them as the main features, but they certainly were a lot of work. And then the last set of major extensions we added were some changes to the way classes work with respect to when they're constructed and when they're destroyed, and especially when you throw exceptions from within constructors. There are some differences between C++ and Pascal. So if you want to inherit from a Delphi class, if you want to inherit a C++ class from a Delphi class, you have to have some different semantics, which actually break the rules of C++. But it's really important to implement them according to the Delphi standard, otherwise the Delphi runtime libraries won't work. So we put in some extensions to support that as well. And then...
oh, go ahead.
And then that was done all on the 32-bit side way back when, and then we ported all of that work or implemented it on top of the client compiler when we did the 64-bit port.
Right, so all this years of development effort on compilers and what we learned about working with the types of frameworks that we use for visual development, for example, we brought into the client compiler. Yeah, so let's talk a little bit about the language extensions in particular. There are almost every C++ compiler vendor who has a framework does some extension to the language. And, we've seen, of course, Microsoft with Managed C++ do some, they've added properties, for example, and a couple other symbols for things. Why did we choose to do it the way we did with the double underbar, and what do some of these specific extensions mean?
Well, we chose to do it with the double underbar because, well, if you do it, and the double underbar was really the way that you keep a name in the vendor's namespace. So your average user is not supposed to define symbols that start with a double underbar. We chose to do it as an extension as opposed to trying to do it with, well, there are other ways of doing properties. So, for example, you could do properties by convention, right? You can name properties with setters and with a particular style of naming for setters and getters. You can, in C++, you can use template members as to implement something like properties. The thing is, for Delphi, when you have a class that can participate on the design surface, the properties are actually represented in the runtime type information. And there's quite a bit of information about them in the runtime type information that the designers use to help you edit that property or edit the component on the design surface. So we decided to use this extension so that we could have much better control over the runtime type information that had to be emitted for the designers in order to be able to work. Doing it with C++ extension, with purely as a standard C++ template, or doing it as a convention would have resulted in something very clunky and not particularly attractive to the users.
So we utilize the mechanism to add standard extensions to the C++ language. And the C++ language, to some extent, does provide, a way to define these things, which is how we approached it at the time. Like for instance, in C++ 11, there's I guess you could say, an exercise left to the reader where they provide an ABI spec for garbage collection, even though that's not an implementation that's required for a C++ standard compiler. So let's talk a little bit about, you mentioned runtime type identification, and compared to some other languages out there, like say Java and C# with reflection and the other terms they use for RTTI, C++ really hasn't had as rich of an RTTI specification. Mostly just casting operators. So, why is RTTI important for what we were doing? And, let's talk a little bit about what that means for C++ developers in particular with regard to using our frameworks.
Yeah, C++ type information is actually amazingly simplistic. The public interface for C++ type information contains 2 or 3 methods: one to get the name of the type information, one or two to compare whether or not type informations are equal, and one to compare whether or not one comes before another one. And I don't actually know what you would ever use that for. And the one that returns a name actually can return a mangled name for the type. So it's really not a very terribly useful interface. For a rapid design environment, the type information, the first type information that we came out with described properties, their types, a few other things about them, and the methods that you could use for event handling. And without that type of information, it would be really difficult to do form design. So you want to be able to describe to the runtime enough about an object so that the runtime can manipulate the object without actually knowing about the source code for the type. So we will describe in the runtime type information the type of the properties, the types of methods, and nowadays we'll describe the types of parameters, the types of fields in objects, so that with the Delphi type information, you can actually do full introspection into the type to learn pretty much everything you can about it. They use it for essentially scripting Delphi objects now, and you can do the same thing with C++ now.
So it'd be really easy to add a scripting language binding to C++ with this extension.
Yep, pretty close.
So how does RTTI work then? I mean, in addition to the language extensions, it sounds like we have to generate a bunch of this information into the compiler, and this is obviously something that we had to bring over to Clang in order to make it work.
Yeah, we had to do quite a bit to the runtime type information is generated into the object files. It's data that's available at runtime. When the compiler emits the type info for an object, it walks across all of the methods and all of the fields and emits binary data describing the, as I said, the types and the names of the fields, the names of the methods, and whether or not the thing is a property, whether or not the thing is an integer, whether or not it's a pointer to some other type. And that data is then, it's in a fairly dense binary format within the image. And the runtime library, specifically the Delphi runtime library, has a ton of code to crack that data and serve it up to you with a very nice object-oriented introspection interface in the system.rtti unit. That same runtime type information is used by the streaming system. When you load a form off of disk, the streaming system will read the descriptions of the components that are on a form, and it knows the names of the types, and it knows the names of the properties and the values that that you stored at design time in those properties. And so it can actually take the name of the type, look up the type information for that object, call the constructor, the pointer to which the constructor is in the type information available to the type information. So you can dynamically create one of these objects given just the name of the type at runtime. And then once you've got this object created, you can look up property names, the information about the properties by querying the type information for the names of the properties. And it'll return back little descriptors which describe where the offset of the field is in the structure, or what method you need to call in order to set the property, and what type it is, so that you can pass the right values to the setter for the property if there is one, and fully initialize this object.
Yeah, and I think this is, we just got a comment from Robert out there that, he thinks this is a huge selling point for our product in our C++. The kind of RTTI we do is a big deal for developers because it allows them at runtime to basically do the kinds of things that we do at design time inside Rad Studio. So thank you, Robert, for that comment. And just out there to the rest of the audience, feel free to make comments or ask additional questions, of these guys while we have time with them. And I agree with you, Robert. I think that this is obviously an area where we spend a lot of effort, because in addition to supporting the standard language, we need to support this visual design time environment and the frameworks that deliver it. And so this RTTI is something that's well above and beyond what a traditional C++ compiler would provide. And so this is something that we've built into Clang at this point, and I think that's a pretty big deal. So let's talk about some other things about language interop, Eli. Delphi has a lot of facilities that are very modern, the RTTI being one example. There's different notions around how we deal with exception handling between the two languages. How do we deal with that inside our C++ compiler?
So first of all, first of all, this is going to be the first production Clang implementation on Win64.
Right.
There was some rework that we had to do to make exception handling for C++ in general work on Win64, just to make it participate with the structured exception handling system that Windows uses. Windows has a system designed well, I don't want to say in the operating system. Well, it's close enough. It's in the operating system for handling stack unwinds, for describing the location and length of every function that's in an image, and describing all of the data about all. For each function in the image, there's a bunch of information that describes how its stack frame is set up, and if that stack frame is, if you have that stack frame on the stack, what do you have to do to unwind that frame to get to the previous frame? So Windows has this built-in and codified as a specification, and vendors that provide tools on Windows really need to implement that. If they don't, exception handling in general won't work, and your applications can be pretty unstable if under certain circumstances. The advantage to all this nice unwind information is that you have this really perfect ability to crawl a stack. So in the debugger, where under Win32 you used to have this situation where it was kind of iffy about whether or not you could accurately unwind from one stack frame to a previous stack frame. You might skip a few. You might not be able to accurately do it. In the debugger, we had this problem all the time, where sometimes your stack crawls would look good and sometimes they wouldn't. In Win64, that's really not the case. In Win64, now you generally have a really pristine stack crawls, because of this unwind information that's part of the operating system standard. So first thing we did was we implemented that information, the unwind information and the information that describes the layout of the functions in the image. And then we took the C++, the libc++ ABI that is part of Clang, and we did a variant of that that's built on top of the Windows structured exception handling APIs. In Windows, when you throw an exception, whether it's an C++ exception or another, you actually call an operating system API to do it, and at that point you actually have to play by the rules of the operating system. And so we had to hook up the runtime library code that originally came from Clang, from LLVM, well, from Clang for C++, and make it play nicely with the Windows APIs. Once we got that done, we could set about doing the Delphi interaction. And the Delphi interaction really consists of two or three pieces. One, you want to be able to catch Delphi exceptions and throw them. Two, you have to be able to handle certain semantics for if you throw a Delphi exception from within the constructor for a C++ class. And then the last real feature is in Delphi, they support if you get an access violation or a divide by zero or some other hardware violation, they'll wrap that up into a language exception and reissue it as a language exception. So we wanted to, with 32-bit, we had access to that, and we wanted to do the same thing with 64-bit. So for the constructors and destructors, the really interesting part there is if you are in a C++ constructor and you throw an exception, or any API called from that constructor throws an exception, In C++, you'll only destroy the base classes that have already been constructed. In Delphi, the rule is you call all of the destructors for all the bases, regardless of whether or not you finished constructing the class. So we had to make some changes to the compiler and the runtime to support that. And then for throwing and catching exceptions, the sort of model that in C++ that's that we tend to describe as call it a best practice is to throw an exception by a value and catch it by a reference. Generally, you don't see people throwing exceptions by pointer and catching them by pointer. Sometimes you'll see people throw exceptions by value and catch them by value, but the one that's most common is to throw it by value and catch it by reference. So it's the odd thing about that is that for Delphi, all the Delphi objects are heap objects only. So if you actually try to allocate a local that's a Delphi class, or declare it as a value object in your data segment, you'll get an error because they have to be created on heap, and you can only carry around pointers to them. That was a little bit odd for C++ users who are used to this notion of throwing exceptions by value and catching them by reference. So we made some changes to the compiler so that you could follow that C++ paradigm or best practice of throwing exceptions by value and catching them by reference. So that underneath the covers, it actually converts those things to throwing by pointer and catching essentially by pointer, so that we can satisfy the Delphi RTL, but still make things fit a more normal C++ paradigm. And then the last bit of support we added was pretty much entirely in the runtime, where if you do catch, if you do have an access violation in the C++ program, and you've linked in the appropriate bits of the Delphi RTL, we will catch that access violation or the divide by 0 or what have you, and we will wrap that up in a, we'll have the Delphi RTL wrap it up as a language exception, and then we'll reissue it as a regular old language exception. The one thing that, I don't remember if we actually deprecated this a while ago, but I think we did do it away with this back when we did the OS 10 port, but I'll state it again here, is we used to let you catch stack faults, and we're not going to be supporting that anymore. That was really misguided. It's very error prone, and so you can still catch all the old exceptions that you used to be able to catch, divide by 0, access violation, but no stack faults.
Like a Stack Overflow, for example?
Yeah.
Okay. So how does try finally fit into all this?
Yeah. One of the extensions we did for the Win64 work was underbar, underbar try, underbar finally. This is a feature that we really wanted in C++ for a long time. It makes a lot of code so much easier to write. It's code where you're managing resources. There are lots of places where you can save things in smart pointers and have them automatically cleaned up, but there are a lot of other places where within a function you may want to start some operation and then end some operation. or enter some state and exit some state, and it's not really reasonable to do it by storing some local object with automatic destructors to do the cleanup or finalization of the state for you. An example would be some database operations, or any place where you're going to change the state of an object and try to do some operation, and then you need to change the state of the object back before you exit the scope in which you're doing this. It's some place where you really want to try finally. So we did carry that over into the Clang compiler, just as we had it in the 32-bit compiler. We also implemented underbar try and underbar accept for Win64. Those are Microsoft Windows only extensions. Those are the so-called original structured exception handling extensions that Microsoft had for catching access violations and any exception that was raised by the operating system in Win32. We moved those up to Win64 and have them supported in Clang as well.
So an observation that I'm going to make is that this is in reference to with this announcement about our new compiler architecture. And I saw one, most people are very excited about this. I saw one reporter who thinks it's a good thing that we're moving in this direction, but kind of he lamented that, oh, it means, Embarcadero is not doing compiler development anymore. I'd say I have to disagree with that. It sounds like there's a tremendous amount of compiler development that's being done, and we're bringing a lot to the Clang infrastructure in the work that we're doing as well.
Oh, yes, definitely.
So let's talk about that, this new tool chain a little bit. Maybe you can walk us through the key component parts of it, and what does this mean for people who are developing Windows applications? I mean, what kind of things are they going to be maybe surprised about? Just one example might be using .a instead of .lib. What other kinds of things, as we go through the component parts of the tool chain, do you think that will be interesting or surprising to developers on ECC 64?
Well, I guess it depends on where you're coming from. If you're one of our 32-bit customers and you're stepping up to the new tool chain, there are a few things that you'll see that are different. You mentioned the .lib versus .a. For this tool chain, we're using ELF as our object file format. We could have used COF. We had a lot of tooling already around ELF from back when we did our Linux tools many years ago. And there's not any real particular advantage to us to reading COF OBJs, mostly because for the COF OBJs that you get from Microsoft or C++ are pretty much useless to us because the Microsoft C++ API is not open, and they've never documented it and never will. And pretty much all of the other libraries that we get are all import libraries, and those are trivially produced from DLLs. So we don't get any particular win out of COF. So our customers will see this shift to ELF. With the shift to ELF, we do away with some irritating issues that we had with the old object file format. There were some limitations with respect to the length of public names. So you used to get this irritating bug where names would get truncated and you wouldn't be able to see the fully unmangled name. That's gone now. You should be able to see the full names in any of your map files or any of your object file outputs. That's a small thing. The tool chains, the first major thing that people are going to see is that the command line's different to BCC 64 from BCC 32. And we went back and forth on this a bunch of times. The BCC 32 command line is very specific to our compiler. There are an awful lot of options which don't make a lot of sense in Clang. So we carried some options forward, but most of the command line options are going forward for 64-bit will be the Clang options. They have a really, really wide set of options, and they will be expanding them more in the future. And that just seemed to be the best way to go. So that's one of the biggest changes to customers who actually use the command line compiler will see. The linker is relatively unchanged from previous incarnations of the product. There are some changes to the tooling for generating libraries. There's a TLib 64 now, which generates the 64-bit ELF archives. And the old tools, impdef and implib, there's a new variant tool called MKEXP, make exports, that takes the place of those for 64-bit. And let's see, what else will they see different in the toolchain coming up?
Well, let's talk about the command line switch real quick. Like dealing with include files, I think, is a big one. Is that something that they really need to worry about if they're using the IDE? I mean, and Bruno, I see you nodding your head. Feel free to jump in if you'd like to. But those are, I think, the kinds of things. Especially, what if they're outside the IDE and are building, automated build systems? What are the kinds of things they would need to do in those situations?
Yeah, I'll let Bruno talk about the include switches. If you're using the IDE, for the most part, they won't have to worry about the command line switches to compiler. We did our best to make that work, that part work automatically. The include switches are a little bit different, and I'll let Bruno jump in there.
Okay, so the issue with the includes is that BCC had only one. BCC 32 has -i. It's for everything. Clang, like other compilers, let's say GCC and so forth, have iSystem and then -i, and then iQuote. And usually it doesn't matter. I mean, it matters where you put certain things, but what matters the most is iSystem is given some slack because that's the system headers. So if you use -i for our system headers, you might see certain warnings that you wouldn't see if you put them under iSystem. iQuote is really important because when the compiler goes to resolve quoted includes, so what we call local includes, let's say. Okay, so we used to put those in -i also because BCC 32 has a different logic of how, first it looks for in the current directory. Mm-hmm. Which is actually, I should point out, BCC 32 looks in the current directory, whereas BCC 64 looks in the directory of the source file, there's a subtlety here. If your source file is in the project directory, that's the current directory. We're talking about the same directory. But let's say your source file is, 2 levels underneath, away from your project.
Which isn't that uncommon.
Which is not very uncommon because your project might have a subdirectory called source. Now, BCC 64 will only look in the directory of the source file for quoted includes, whereas BCC 32 will look in the current directory. And so now iQuote matters because if you have a quoted include of a header that happens to clash or has the same name as one of the system headers, I'm just making that up. Let's say you have mem.h, in a subdirectory and you want to do an iQuoted version of it. Well, that's great, but then someone else later let's say the system headers need mem.h, if you didn't use iQuote for that directory, let's say you use -i, uppercase I mean, or -i system, God forbid, but now the system header might be picking your mem.h. I mean, I'm just kind of, so it does matter. It's actually a little harder. It would be easier if we were going from 3 switches to 1.
Right.
Now we're going from 1 to 3, so it requires that you think about how to split them correctly. We will do the system one by default. Like, we will do the RTL, the SDK, the CRTL, the VCL, the FMX. We'll put those in the right place, and even Boost. But if you have third-party libraries and other things like that that you're using, and you are just used to just throwing those on the -i switch, you might want to rethink that. I mean, maybe some of those should be on iSystem. And if they're really local headers that you have, just something that's just used locally for this project, then iQuote would be the one to use. So,
is there a difference in the search order between the two compilers?
The search order, yes, there's a difference because, of course, I mean, you're talking about 3 different switches there.
Right.
But it's not something that I could, like, I wouldn't be able to explain it like very clearly because it totally depends on what's being searched for, from what location, and what are the settings that you have. I mean, if you think of it that way, I mean, someone was telling me here, like, you know, system include, you know, all your standard, you know, C standard lib, C standard IO, and all your vectors and all this stuff. iQuote are the things that you would be quoting, and then -i are probably like third-party libraries that you want to treat like system include, but they're not really system include. So meaning, like, let's say a library that you ship, you want to make sure you catch all the warnings. So there's not that much difference between iSystem and I. It's just the little slack that we give you for, I mean, the compiler gives you for warnings. So.
Okay, thank you. Along those lines, you know, we've done a lot of work in BCC32 around precompiled headers. And maybe this is another question for Bruno, but what are some of the differences there that people might need to be made aware of between dealing with precompiled headers in BCC32 versus BCC64? Yeah,
that's something that we talked a lot as a team, how we would do it, because BCC32 had a really, really nice way of handling precompiled headers. A little too nice, I would say, because it was too nice in the sense that it allowed our users to not set up PCH correctly and kind of get away with it, and then performance would not be very good, and then they'd say, oh, you know, code completion is slow or something like that. I mean, code completion can never be as fast as it should be. I agree with that, but you can also help by setting up correct PCHs. BCC32 had a really, really nice way of doing PCH. Basically, it handles everything. You know, you just say, I want PCH, and it generates it, and if you have files having includes in not the same order, it says, okay, I'll create another one. I mean, it's just very, very flexible. With BCC64, we opted to use the Clang approach. We first considered whether we would try to build a BCC-style PCH. There were some drawbacks to doing that way, not just the fact that it's worked, but also there is a precedent for the code completion in Clang does that with preambles, but it wouldn't be able to do the nice part, which is where BCC can essentially have multiple precompiled headers in one PCH file. And so then we reverted back to going the Clang approach. I think in the long run it pays off. You have to set it up yourself. So for people who've used, let's say, Visual Studio, you're familiar with standard AFX.
Yep.
So it's kind of the same idea. For every project, you will have a header that's your PCH header. That header will be compiled explicitly once. It will be compiled into a binary file, which we call a .pch, actually. So you have let's say I have my pch.h. We will compile that once, and then you get my pch.pch, okay? And then every other source code in your project will use my pch.pch as a include PCH file. The IDE handles that nicely for you. If you're on the command line, you have to do it yourself. I mean, unless you use our MS build scripts. But if you, let's say you are on the command line and you call the compiler yourself, or you use make, then you would want to do that yourself. I mean, you have to basically do those commands. It pays off to set it up, but it requires a little bit more setting than some of our users might be used to, because with BCC32 it was really kind of handled automatically. So.
Right. And to some extent, what I hear you saying is that even though things are changing, it's going to be for the better. I mean, one example is with regard to language compliance. Even though BCC 32 might let you get away with some things, and BCC 64 doesn't, it's going to make your code better. It's going to make it more compliant.
Yeah, that's been the general feedback. Is usually, oh, I like that. It's catching things in my code that I didn't even know I did incorrectly. That's usually the general feedback.
Good. Okay. So Eli, we talked a little bit about the new binary formats. Does that mean any changes to debug info? I mean, what about folks that might be reading or trying to crack our binaries to do performance analysis tools or something along those lines? What can you say about those kinds of things, or even just is there anything they should be thinking about with regard to the change, or is it sort of something they don't really need to worry about?
There's there's good news and there's bad news.
Let's start with the good news.
It's the good news is the bad news. The debug format is DWARF. In particular, it's DWARF 3 right now.
Okay.
And the good part of that is that it's a very well-defined standard, and it's pretty mature. And there's a couple of bad parts. The bad part is it's totally different from our 32-bit debug information format, and it's fairly large, which is ironic. Our 32-bit, and this was actually a joke from a long time ago, our 32-bit debug information format's called Giant, and and it's actually a lot smaller than DWARF.
Smaller than the DWARF. Kind of timely for The Hobbit coming out this Friday.
Kind of. There are some interesting, nice things that we get out of DWARF debug information. Macros, for example. DWARF has long had support for describing macros, and so you can actually get the values of macro expressions in debugger that's using DWARF and knows how to support that data. We never had that in Giant. We always thought it would be nice to have it, and now we do. Internally, we are using the LDB project for an evaluator, and that project has a full understanding of the Clang ASTs. They actually use the Clang ASTs for doing the evaluation. It's very sophisticated, and it takes full advantage of the DWARF information that the Clang compiler that LLVM puts out. So we can provide links to the DWARF standard for people if they're curious. I don't have them handy for this webinar right now.
Well, I mean, your point is, I think, a good one. That it's good news, and that it's a standard that people can work with, and it's not. They don't have to rely on us to document or do any kind of text editing to figure out what the format is.
Yeah, and there are free libraries for reading and parsing that information too. Silicon Graphics, for example, put out a library called libdwarf a while back, so you can. And that's an unencumbered library that you can use for reading that debug information. And of course, the Clang toolchain, the LLVM toolchain, has readers in there, but they're a little too tied up in LLDB and friends to be as useful as something like the Silicon Graphics libraries.
So we did get a couple questions, and I'd like to bring one up right now. And this has to do with tooling, which is obviously part of this discussion. It has to do with code completion. The question is, how should I set up my header file sequence to get the best performance with code completion? And does that matter?
Well, the best way to set up code completion is to ensure that you have a good precompiled header. And with BCC32, that was always the case. And it didn't help that that we actually created all projects and assumed that vcl.h was your PCH file. And basically, we say pound include vcl.h, and then we put pound pragma header stop, which tells the compiler, that's it, don't precompile anymore. And therefore, when you start bringing in STL or boost or even more VCL headers, those things are not being precompiled, and precompiled header would be, the precompiled header doesn't have a lot of the symbols, and therefore code completion would not be very performant. You get a huge boost by setting up a good PCH. We have a PCH wizard that tries to figure out pretty much which headers should go in your PCH file, but it can't do it. I mean, it fails in lots of cases. We have projects in-house, and for good reason, because you can do all kinds of ugly games with headers in C++ or C, when they rely on particular order or
circular references.
Yeah, that kind of thing. And so therefore, or you include them multiple times with different defines. And so, I mean, there are headers that are meant to be like that, but assert and the pop packs but the best thing for code completion is to have a good PCH file. As far as the BCC64 side of it is concerned, that also applies there. We are still working on that aspect of BCC64. My personal usage of code completion in BCC64 is that it's not as snappy as BCC32 when I've set up a good precompiled header in BCC32. So
we still have some optimizations to do.
Yeah, there are some things that we will need to be looking at, and we've started to look at those things.
So we're obviously using the Clang front end for this purpose.
Yeah, actually, we're not using not only the Clang front end, but there's a library from Clang called libclang, which is actually a C-based API for doing exactly that kind of thing, code completion. Well, they do other things also, syntax highlighting and find references. That part we actually, so there's no, that library is meant for IDE interaction. What we've essentially done is we've built, if you want, a copy of libclang with more than what Clang itself puts into libclang. We put kind of the whole compiler with all the backend, LLVM, and the code gen in it. But for that part of the code completion, we're using the Clang Code Complete, which is the API that anybody who wants to learn how to do code completion with Clang, there are people who do that, like with Vim or Emacs out there. That's exactly what we're using. Yes. Yeah.
And are there some good resources, or maybe we can provide some later, for setting up PCH files for the optimal performance, or is certain rules to follow? I
will verify with the documentation team, and we've talked about it. I don't know. I'm assuming there are some rules. I mean, the idea is you put everything that's constant in the PCH file. Because we have only one PCH file at the IDE level, that might not be possible, in the sense that maybe half of your project is really business engine and you use a lot of library A and library B, and then half of your project is the GUI portion, and there you use FMX or VCL or whatever. And so now you're torn. You don't want to create one PCH file that's got everything in it. Maybe you'd want to keep the business side in one PCH file and the GUI side in another PCH file. So ultimately, we would like to have the IDE handle multiple PCH files. But for now, put everything that's not changing, that's stable, and you have to balance it. I'm sure there's a tipping point. If you put too many things in the header, you might you're not getting the benefits out of it. So
somebody had asked, what is BCH? And it's actually PCH, stands for precompiled headers. So thank you, Andrew, for that question. Another question came in that asks, well, with the old with BCC32, I could build basically one big exe. Doesn't depend on any external files. Can I do the same with BCC64? And yeah, the answer is yes.
Yeah.
So it's just static linking to the libraries that we provide and any other libraries that you may need to interact with. Of course, they need to be in the same format, .as or .lib, so you'll need to have compiled them with our toolchain in order to do that, but you can absolutely build one single exe if you need to.
I mean, technically, they'll still depend on things like kernel32.dll, but those are all things that are just part of Windows.
Right, exactly. So So this is interesting. The toolchain, it sounds like it's become, and part of it's because of Clang, obviously, like it's become more like other compilers, if you will, out there in the world in the sense of the way it deals with PCH, the way it deals with debug info, a lot more standardized than our previous versions.
Yeah.
So, go ahead, Eli.
Yeah, I guess I don't really have too much more to add to it. I think the PCH mechanism is a little bit different. Knowing what I know about the architecture of the Clang compiler, I would say it's not exactly classical. I'd say it's a very modernized toolchain. This is something new. It's got a whole bunch of libraries on top of it that are going to allow for new tooling. That's we're already seeing it. It's going to for refactoring. We hope to get great gains out of it for that. This is a different kind of an environment.
And of course, the biggest advantage to our end users and for us as well is that we can much more quickly than we ever could have with our previous architecture target new CPUs and new operating systems.
Yeah, the back end is pretty impressive back end. It's got a whole bunch of targets already done for it. There are ARM targets. Somebody did a code generator for the NVIDIA GPUs.
Yeah, that's cool.
NVIDIA is doing their own version.
Makes me want to go out and buy a new NVIDIA card.
Yeah, and the optimizer is very good. I don't think we have official benchmarks yet for our tooling, but it's a lot better than our current optimizers by a long shot.
When I was in Korea last week, I did see one of our field engineers had done some benchmarking with Drystone and Whetstone to see what floating point performance and integer performance was, and it was substantial. A couple more questions coming in. I guess this is more just a question on you guys having to deal with the new toolchain, but was it easier to generate HPP files from Delphi units with the new toolchain, or is that making it any harder or different?
Generating the Delphi units from the new toolchain is no easier or harder. There was actually a lot of work in the Delphi toolchain to get it to generate the new mangled names for to satisfy the C++ ABI to match the mangling that Clang generates. But on the C++ side, everybody who has worked on the compiler has found it, I hesitate to use the word infinitely, but what the heck, I'll use it, infinitely easier to make modifications to this toolchain, to fix issues, to add features. It is a much nicer toolchain to be working with, much more efficient to be working with it.
Along the same lines, the same person asked, in the 64-bit compiler, then, are there any restrictions in Delphi constructs that I can use, or should I avoid any? I mean, is the interaction different? Thoughts, Eli or Bruno?
Bruno?
Well, it's the same issue. So there are certain things. Usually I go at it from the other angle. I say there are certain things in Delphi that you shouldn't use if you want your code to be consumed from C++. Okay, for example, don't expose generics in your interface section. You can expose generic, like a variable is already of a generic type, an instantiated type, but don't expose like a new type that's what we would call a template type def, for example, in C++. And there are other things like that, like when you do closures, there are certain list of types that you can put in there. Anything that would trigger generation of RTTI, you have to make sure that it stays within the bounds of what the C++ compiler can handle. Like, again, don't put generics inside of a closure. That's not because the C++ compiler can handle it. It's just that RTTI information, when it makes it to the IDE and the user double-clicks on that event handler, the IDE is not sophisticated enough to give the user event handler that has the signature with all the generics in it. So so there are certain things. There's a realm where you can write code that's. I have a page that I've written called like writing C++ friendly Delphi code. So as long as folks stay within that, that subset of Delphi code, it's fine. You can go either way. So
Okay.